I'd like to thank the organizers for inviting me. It's a pleasure to be here. This is joint work with my colleague Jisoo at Michigan and our PhD student Yuan Zhang. Luckily for me, there was a lot of discussion of this yesterday, so I'll go through my introductory part relatively quickly, but still I think for a lot of people the general introduction might be more interesting than my particular thing about overlapping communities, so I'll tell you some general facts. Community detection is a very well-studied problem. There is an enormous literature in it, coming out of physics and computer science, and more recently joined by statisticians. Just like in clustering, communities don't have an easy definition to write down. People say they think of communities as cohesive groups of nodes in a network. What does that mean? Is up to interpretation. A common interpretation, but by no means the only one, is having many links within one community and fewer links between to other communities. And typically, the community detection problem is defined as a partition. So you take each node in the network and assign it to one and exactly one community. But in reality, of course, it's often more complicated and communities overlap, and that's what I'll talk about later. Just a few examples of networks where people want and do community detection. There are many examples all over the place. Social and friendship networks, social scientists study that, why people become friends and what do they have in common. Citation networks, collaborations, you find communities. Recommender systems, you find groups of products bought together so you can recommend them. In neuroimaging, there's a hot new field of connectomics. You're trying to understand brain networks, you find regions that work together. In biology, people look at gene and protein networks. In ecology, people look at food webs. Those are also networks, directed networks of predator-prey relationships. And you find communities in those. In infectious diseases, you study how diseases spread through community. And of course, in security, there are obvious applications. So the NSA funds a lot of this research, not mine though, just to be clear. In basic notation, I'm going to focus on the simple case of unweighted, undirected network, though a lot of what I'm talking about can be generalized. So the data we observe comes in the form of symmetric and binary and by an adjacency matrix. And our goal is to estimate the unobserved labels for every node that take values 1 through k. The question of how you choose k is an excellent question. It's an open question. There have been some proposals, but I'm not going to talk about it. So we're just going to assume that k is chosen by the user. And if we're talking about models for this network, then typically what it means is we set up some definition, some model for the probability of an edge. Almost universally in this line of work, edges are assumed independent. So once you define this probability, you're done. This assumption rarely holds in practice, but that's another story. I will follow it and assume the edges are independent. So the stochastic block model came up before, so I don't have to explain it. This is how I'm going to write it. This is going to be convenient for me, encoding the membership as a vector of length k with just a single 1 for the community that the node is in. And one feature of the stochastic block model is that knowing which community the node belongs to determines its behavior completely. So all the nodes in the same community are equivalent to each other, probabilistically. And that's not a good feature in practice because in reality, there's usually heterogeneity. And one particular limitation of the block model that people have worked to address is expected degrees. Under this model, every single node in the community has the same expected degree because they're all the same. And in fact, they follow the Poisson distribution. It's easy to show. But what we often see in real networks are hubs, or the small world phenomenon. There are a few people who are very well connected, who know everyone, and everybody else is connected through them. So, something that's been proposed to address that particular limitation is the degree-corrected stochastic block model, proposed by physicists. They basically add these extra parameters here. So now these parameters are node-specific. Each node has its own factor that can be used to inflate its probability of connecting, and that represents its degree. So a hub node could have a large theta and connect to a lot of people. This, of course, doesn't come for free because suddenly you have n extra parameters to estimate, and before all your parameters were on the order of k, but it does address that limitation. And this is how you can write it in matrix form, so just an extra diagonal matrix around the block model. The example that's quite well known by now that was used to motivate this particular correction is this data set. It's actual data. This is political blogs all about US politics. The data set was collected right after the 2004 presidential election. The links represent the web links from blogs to each other. Direction is ignored. The color represents a manual label that was assigned to each node by the people who collected the data as liberal or conservative in the usual way. And you can see this is actually plotted with the size of the node representing not even the degree but the log degree. Because if it was the degree, you just wouldn't see the rest of the nodes. So the degrees are extremely heterogeneous, but there are clearly communities, as you would expect. And so this is the difference between fitting the stochastic block model and the degree-corrected stochastic block model. The stochastic block model, because it needs the degrees of the nodes in the same community to be similar, will put all the large degree nodes together in one community and all the rest in the other community. And that's not unreasonable. It's also a partition into sort of influential blogs and more the peripheral blogs. But that's not the one that corresponds to the labels. And this one actually does fit it relatively well. So this is also something that has been discussed yesterday. I'll just briefly mention the two fundamental difficulties about community detection. First of all, in principle, there are k to the n assignments of community labels. So in principle, it's an NP-hard problem. Although, of course, there are many algorithms that have been proposed. And the other fundamental problem is sparsity. The sparser the network, the less data you have, the data are edges, the harder it becomes to estimate. So the theory, which again, I'll just briefly repeat. There were two talks about this. Yesterday, I'm stating this in the form of Mossel, Niemann, and Sly. Latest result, Afonso gave a slightly different interpretation. Basically, what it says that even detection, even finding some correlation with the solution is only possible above some threshold. And then if you want to have consistency, you need the degree to go to infinity, essentially. The talks yesterday were about exact recovery, which is also known as strong consistency. I'm personally entirely happy with weak consistency, which is just saying the fraction of errors goes to 0. That's what we would maybe typically do in classification. That requires a slightly weaker condition of just not faster than log n, but just lambda going to infinity. But still, that's not going to happen with sparse networks. And you can also just see it. If you make a few plots, these are stochastic block models with k equals 2 at different degrees. The structure emerges eventually, but at lower degrees, you just don't see it yet. You can equally see it in the adjacency matrices. This is the same networks, but just as plotted as adjacency matrices. And of course, if you look at it like this, you see it, right? It's right there. Even with lambda equals 1, you see the pattern. But that is not what you observed. You observe this matrix reordered arbitrarily. So that's what it looks like when you observe it. And for comparison, if you look at an Erdős-Rényi graph with the exact same number of edges, that is what they look like, right? So not an easy distinction to make, not by eye at least. So what do we do? So how do we actually do community detection? People do this all the time. Even for the stochastic block model, which is arguably an overly simplistic model, optimizing the likelihood directly is intractable. And broadly speaking, you have two choices. You either do something clever with the likelihood, and I'm listing some algorithms here, roughly in increasing order of speed. So we heard about SDP relaxations. I've actually worked on this too, and it's very interesting from the theory point of view, but it doesn't scale being SDPs. As far as I know, the last algorithm, the pseudo likelihood, is still the fastest, and that can do maybe 1 million nodes in about 1 minute. And belief propagation is also fast, but those two need starting values, and they need a starting value that's correlated with the truth. So you can't just run them agnostically. Or your other option is forget the likelihood, forget that it's NP hard, and just do something generic that is fast and works. And spectral clustering is often the top choice in that category because it's easy to do. So just very quickly to remind you how you do spectral clustering and how people do it with adjacency matrices. The basic idea is very simple. You replace the data matrix with its leading eigenvectors, and then you do k-means on the rows. In community detection, it's typically done on the Laplacian of the matrix. Although in principle, you could do it on either the adjacency matrix itself or the Laplacian, which I'm going to define like that for here. There are many other ways to define it, but that's what I'm using. In theory, both are asymptotically consistent, but in practice, the Laplacian is better. And actually now, in theory, Sarkar and Beckel have shown that there is also, you can actually show that it's better, although it's a difference in the constant, not in the rate. And it basically works for the stochastic block model because if you could take the expectation of the Laplacian, if you look at the population Laplacian, the matrix is block constant, and so its eigenvectors are also block constant, and you just read off the structure. But Spectral, so it's nice and fast, but it's generally known to fail on sparse networks, and more so than other methods. So everything sort of fails on sparse networks, but this spectral clustering is particularly bad. Why is that? Well, if you look at this example, this is a very small, very sparse network. Here it's easy to see where there will be a problem. There are, of course, isolated nodes you can't do anything about, but there are also a couple of isolated edges. The matrix becomes block diagonal with little blocks, and there will be eigenvectors sitting on those blocks. So you see them right there, first and third. This is the constant one. It's supposed to have, the first one is supposed to be the constant, and this is the one that's supposed to be the solution, but it only comes up at number 4, not number 2. So that seems like an easy thing to deal with. Okay, let's just throw out little things, look at the largest connected component. Works here. This eigenvector goes up to the second place where it belongs. But that turns out to not always work. So if you look at this larger network, and this is already just showing the connected components. I've already thrown out the rest. So it started out with 800 nodes. Now it has fewer. This is what the eigenvectors look like. And there is still something here. Even though everything is connected, there is this weird spiky thing. And this is the solution, which we want, but it's not in the right place. And if you go back to the graph and map the spiky thing to where it has mass, you find that it's here, which is a very, very weakly connected part of the graph. It's called a dangling tree. It's just connected by a node. So even though it's technically connected, this thing still happens. And so people have by now proposed, yeah. For the Laplacian, yeah. For the Laplacian. Yeah, everything's for the Laplacian here. So several solutions have been proposed to this problem. This one is ours, so I'm partial to it. It's also very simple. You just add a small constant to the entire matrix. It's rescaled so that this is lambda the degree, so but it's just a constant. Then you proceed as usual. Other things have been proposed. You add something to the degrees. You look at a different Laplacian. You look at the 2-core, which essentially says remove dangling trees, remove low-degree nodes if you're doing the Laplacian. So all these things have been proposed. They haven't been rigorously analyzed as far as I know, except for this last one, but this was sort of in a different context anyway. But what I think they do is, in different ways, they all solve the same problem. They get rid of the spiky eigenvector. So in particular, our regularized one, you add that constant with 0.1, and they just switch. And it's not even sensitive to the constant. You can make the constant bigger, and you will just kind of whiten the spiky thing, and it'll go away, but the solution will remain. So the two, I guess, points from this introductory part that I want to carry on to overlapping communities is degree heterogeneity is important, and the stochastic block model doesn't allow it if you want to fit real data. And then regularization is important if you're going to do spectral clustering. Questions? Well, I'm trying to fit a block model with k equals 2, right? So no, it doesn't have to be balanced, but I don't want everything else to be in one community either, right? So I don't want to just the tree and everything else. Of course, you could do spectral clustering not just on k eigenvectors, but say on 2k, right? You could keep more eigenvectors, but then you're also adding noise. So there is some trade-off. You could, instead of regularizing, you could just say, okay, you know, the right eigenvector is somewhere down below. Let's just take more of them, but just make it worse. Okay, so now to overlapping communities. A lot of this literature came out of social networks, and this is the context in which people think about it. And say if you think of Facebook or something like this, people typically have many communities they belong to. They could, you know, they have their friends, their classmates, their neighbors, colleagues, etc. But you don't know why they're linked in a network, right? You just see that they're friends on Facebook. You don't know why, and often there is more than one reason, right? There's more than one thing. So as with non-overlapping communities, you have two broad choices. You can model it, or you can just do some generic clustering. I'm going to model it because, you know, I'm a statistician. But I do want to also keep in mind the computational cost, and so implementation will be via spectral clustering in the end. So going back to the political blogs example, this was the data, and this is how we fit it so far with the degree-corrected stochastic block model. But, you know, possibly it might be more interesting to fit something like this, where the nodes that are sitting in the middle that link to both, you can actually sort of give them two colors, and the size of that is important too. You can tell, like, how much is it blue, how much is it red. Given this is American politics, the actual intersection may be very small, but at least in general, could be of interest. So let's go back to the two models we've talked about so far, the stochastic block model and the degree-corrected version. People have thought about how to incorporate overlaps into models like this. This is a fairly natural extension, overlapping stochastic block model. Instead of allowing just one entry equal to 1 in the membership vector, just toss a coin for each one. So you can get all ones, you could get all zeros, so you could get nodes that are just not in any community. There's another well-known model, the mixed membership stochastic block model. This is sort of a different kind of thinking. Here they don't fix a membership vector. They draw a new one from this multinomial thing with a Dirichlet prior every time a node talks to another node. So like when I talk to one person, I could talk to them as a friend, but when I talk to another person, I could talk to them as a colleague. So that's really different philosophy. That's not having a fixed membership, so that's not going to be what we do. And there's another, this is a very popular model also coming out of the physics literature. So what they did is they relaxed the membership vector to have non-negative entries. So you're no longer just in or out. You could be more a member of one community than another. And then they just completely got rid of this B matrix and of everything else. So it's just this product of Z times Z transpose. So our goal in setting up an overlapping community model, so we wanted to sort of keep the best of all of these things. So we wanted it to be flexible so that a node can belong to a community strongly or weakly, so it's not just binary. We need it to be identifiable. This is something the physicists don't typically think about, but in the end, we only observe A, so all we can estimate is its probability matrix, and we better be able to identify the memberships uniquely from that. We want it to be interpretable, by which I mean I would like to keep this matrix B that disappeared here. Because if I have the matrix B, I can say this community 1 is tighter than community 2, and they're more related to each other than to community 3 and stuff like that. If all I estimate is the membership vectors, I can say something about the nodes, but I can no longer say anything about the network structure at the community level. And then we want to be able to deal with heterogeneous degrees, and we want to be able to fit it fast on a large network. So putting all of these things together, this is what we proposed. There's nothing really surprising here. So we're keeping the membership vectors. We're relaxing them to have non-negative entries. We're also going to keep the degree corrections. This scaling constant in front is mainly for theory, so that's not really important. And we still have the matrix B, that is K by K, that encodes community structure. Of course, this is not identifiable by itself, right? I have this ginormous product. And in particular, I could stick a rotation in there and rotate everything, including the membership vectors, and nothing would change. So I do need constraints to make the model identifiable. These are sufficient conditions, so they may not be the tightest, but this is certainly enough. The first two is not really conditions. This is just how we define it. So we define the rows of Z to be all norm 1. The average of thetas to be 1, that's just for remove the scaling ambiguity. The important thing that we need, and the other model that relaxes the binary membership also needs, is to have at least one pure node in each community. So each community has to have something in it that uniquely identifies that community. And then we also need positive definiteness of B, which essentially means it's an associative community structure. Nodes are more likely to connect within than between. Yeah, that's just a vector, so just Euclidean norm. So this is just more convenient for us. You could do the L1 norm, but just turns out that this is easier later on. So this is related to a couple of other things. You can just write it as a product of two matrices, X and X transpose, and then those of you who are familiar with non-negative matrix factorization will recognize that formulation. And this, in fact, has been proposed for overlapping community detection. But of course, if you write it this way, there's no interpretation. But you can still think of that, and that's sort of a useful approximation to think about. So how do we fit this problem, this model? I'll just give you the intuition. Suppose you have a pure node. Forget about these constants. Pure node has a single 1 and all the rest are zeros. So then the corresponding row of the X matrix is just b to the 1/2, the kth row of b to the 1/2. And so then you can think of the rows of the square root of b as positions of pure nodes, the latent positions of pure nodes. That's what it represents. And then everything else is a linear combination of these pure nodes. And so that tells you essentially what you need to do. First, you find these pure nodes, which are community centers, and then you project the rest onto this, and you get the linear combination coefficients. So this is the algorithm. Yeah, you don't know which ones they are. But you need to have one. Yeah, otherwise it's just ambiguous, basically. I need to look at that more closely. I think it's very similar. I think it's the same idea. So basically what you do is you compute the eigenvectors, then you normalize the rows, and this is where the regularization goes. I can already see I won't have time to talk about it, but this is where we regularize, and it is necessary for theory. It turns out it also helps stability in practice. So we add some small constant when we normalize. And then this is the key difference between the usual spectral clustering and what we do here. We apply k-medians instead of k-means. because we have pure nodes and we also have these mixed nodes, right? If you do k-means, it's going to get confused because there are things sitting on the boundary. But if you have enough pure nodes in each community and you do k-medians, it'll still find the right centers. And that's basically it. Then once you find them, you project and normalize because it's supposed to be norm 1, and it gives you the final membership vector. Yeah. So because we sort of like if you have two clusters, right, the pure nodes are here and the pure nodes are here, but there are also points here, actually points here. And so if you run k-means, it's going to get confused by the middle, by the points in the middle. So I'm going to, I know I'm almost out of time. I'm going to skip the conditions, which just to show you the result. We can show that this is consistent in terms of estimating the membership vectors, just in the Frobenius norm, because these are things with non-negative entries. The rate is a little bit worse than what you would need for regular weak consistency. It has to be a little bit faster, but this is a much harder problem as well, so that's not really comparable. I'm going to skip the simulations. I'm going to just very quickly show you an application to data. This is a large collection of social networks at a Stanford website called Snap. There are over 1,000 of them there. They're eager networks, meaning there's one person who labeled all their friends. They're extremely diverse. There are all sorts of things. So we took a subset of them, and this summarizes the subset we took. There are 10 from Facebook, 40 from Google+, 180-something from Twitter. You can see the sort of the spread, and these are the averages over those sets and standard deviations. So there are degrees and so on. This is an interesting number to look at. This is the fraction of nodes that are in overlaps. This cannot be too large for the methods to work. And this is a comparison of seven methods. Ours is first, and there are these various benchmarks. It so happened that on average, it does better in every set. It doesn't do better for every single network in each data set. So like out of those 180 Twitter networks, it doesn't do better for every single one. But on average, it does better. And it's probably because it takes into consideration all these different things that some previous models dropped this or dropped that, and we sort of kept them all, maybe. And just to summarize, the main contributions are the model with all these components, which is still identifiable and interpretable while being flexible. The key insight of the algorithm is to do k-medians when you have overlaps instead of k-means. And conditions, which I skipped, essentially say the network has to be not too sparse and the overlaps not too large. You have to have enough pure nodes to be able to do this k-medians. And there's lots more that you could do. Handling substantial overlaps, we still can't do that, neither in practice nor in theory, or at least not very well. Disassociative community structures, weighted networks, and incorporating node and edge covariates, all of these things would potentially improve performance. I'll stop here.